Last time, we found the null space by setting free variables to whatever values felt convenient, and that works, but it's messy. Some choices give redundant vectors, others produce fractions for no reason. There's a systematic recipe that always produces the perfect building blocks, exactly n minus r vectors, no more, no less, and every solution to ax equals 0 is a combination of those. Let me show you the difference. On the left, the messy approach might give us vectors like negative 4, 2, 0, 0, and 3, 0, negative 3, 3 halves. These are redundant and messy. But the recipe on the right gives us two clean vectors, negative 2, 1, 0, 0, and 2, 0, negative 2, 1. These are independent and complete. Then notice the arrow. The recipe always gives exactly n minus r vectors. Let me show you how it works. Here's our 3x4 matrix A and its echelon form U. Let's perform elimination. Take row 2 minus 2 times row 1 to get 0, 0, 2, 4. Then row 3 minus 3 times row 1 also gives 0, 0, 2, 4. Finally, row 3 minus row 2 gives all zeros, so U equals the matrix with rows 1, 2, 2, 2, then 0, 0, 2, 4, then 0, 0, 0, 0. Now let's identify the pivots. Elimination produced pivots in columns 1 and 3, the one in the first row, first column, and the 2 in the second row, third column. Those are the pivot columns highlighted in blue. Columns 2 and 4 have no pivots. Those are the free columns highlighted in orange. The corresponding variables x2 and x4 are free variables, meaning they can take any value. Here's the key count. N equals 4 columns, R equals 2 pivots, so N minus R equals 2. Two free variables means we need exactly two special solutions to describe the entire null space. Here's the recipe. For special solution 1, set x2 equal to 1 and x4 equal to 0. We activate one free variable and silence the other. Now we back substitute, meaning we solve for the pivot variable starting from the bottom row. Row 2 of U says 2x3 plus 4, x4 equals 0. With x4 equal to 0, we get to x3 equals 0, so x3 equals 0. Now move to row 1, x1 plus 2, x2 plus 2, x3 plus 2, x4 equals 0. Plug in all our known values, x1 plus 2 times 1 plus 2 times 0 plus 2 times 0 equals 0. That simplifies to x1 plus 2 equals 0, so x1 equals negative 2. The first special solution is the vector negative 2, 1, 0, 0. Let's read the column dependence. Negative 2 times column 1 plus 1 times column 2 equals the 0 vector. This tells us that column 2 is exactly twice column 1. Now let's find the second special solution. And this time, we switch the assignments for the free variables, set x2 equal to 0 and x4 equal to 1. Starting with row 2, 2x3 plus 4 times 1 equals 0. So 2x3 equals negative 4. Given x, 3 equals negative 2. Now back substitute into row 1, x1 plus 2 times 0 plus 2 times negative 2 plus 2 times 1 equals 0. And that simplifies to x1 plus 0 minus 4 plus 2 equals 0, which gives x1 minus 2 equals 0. So x1 equals 2. Therefore, the second special solution is S2 equals the vector 2, 0, negative 2, 1. We can verify this makes sense as a column dependence. 2 times column 1 plus 0 times column 2 minus 2 times column 3 plus 1 times column 4 equals the 0 vector. Now we assemble the complete null space. Every solution to AX equals 0 has the form x equals c, 1 times the vector negative 2, 1, 0, 0, plus c, 2 times the vector 2, 0, negative 2, 1, where C1 and C2 range over all real numbers. Let's see what each special solution tells us about the columns of A. The first special solution, S1, has entries negative 2, 1, 0, 0. This means negative 2 times column 1 plus 1 times column 2 plus 0 times column 3 plus 0 times column 4 equals the 0 vector. The second special solution, S2, has entries 2, 0, -2, 1. This means 2 times column 1 plus 0 times column 2 minus 2 times column 3 plus 1 times column 4 equals the 0 vector. Every null space vector is a linear combination of these two special solutions. We say they span the null space. Geometrically, since we have two free parameters, C1 and C2, this null space is a two-dimensional plane passing through the origin inside R4. The recipe works, but why these particular assignments? Let's stack the two special solutions as columns of a matrix N. The matrix N has 4 rows, labeled x1 through x4, and 2 columns, one for each special solution. Row 1 gives us -2 and 2. Row 2 gives us 1 and 0. Row 3 gives us 0 and -2. And row 4 gives us 0 and 1. Now look carefully at rows 2 and 4, the free variable rows. In solution 1, the free variable entries are 1 and 0. In solution 2, they are 0 and 1. That's a 2 by 2 identity matrix sitting right there in the free rows. This identity block guarantees the special solutions are linearly independent, meaning neither is a scalar multiple or combination of the other. Why? Because if you try to write one as a multiple of the other, the identity block in the free rows would immediately give you a contradiction. Now look at the pivot rows, rows 1 and 3. Row 1 has -2 and 2. Row 3 has 0 and -2. This is what we call the negative F block. This entire block structure is engineered by the recipe. If you made arbitrary free variable choices, you could accidentally produce dependent vectors. But the rule of setting one free variable to 1 and the rest to 0 prevents that, because it forces an identity matrix into the free variable rows. To confirm that our recipe works in general, let's apply it to A transpose, which is a 4 by 3 matrix. A transpose equals the matrix with rows 1, 2, 3, 2, 4, 6, 2, 6, 8, and 2, 8, 10. After performing elimination, we obtain the upper triangular form U with rows 1, 2, 3, 0, 2, 2, 0, 0, 0, and 0, 0, 0. The pivots land in columns 1 and 2, so the rank R equals 2, N equals 3 since there are 3 columns, and N minus R equals 1. Right? So that means there is one free variable, x3, and we expect exactly one special solution. We set x3 equal to 1 and back substitute. From row 2 to x2 plus 2 times 1 equals 0, which gives x2 equals -1. From row 1, x1 plus 2 times -1 plus 3 times 1 equals 0. That simplifies to x1 minus 2 plus 3 equals 0, so x1 equals -1. The special solution is the vector -1, -1, 1. The null space of A transpose is a line in 3-dimensional space. Every solution equals C times this vector. Notice what this encodes. Column 3 of A transpose equals column 1 plus column 2. The special solution captures that exact dependence among the columns. Here is an important observation. Now the rank of A equals the rank of A transpose, both equal 2. This is always true. A matrix and its transpose always share the same rank. However, even though they have the same rank, they have different null spaces. Why? Because the null space dimension depends on n minus r, not on r alone. For matrix A, which is 3 by 4, the number of columns is n equals 4. With rank r equals 2, the null space dimension is 4 minus 2, which equals 2. That means the null space of A is a 2-dimensional plane sitting inside R4. The two special solutions, S1 and S2, span this plane. For A transpose, which is 4 by 3, the number of columns is n equals 3. With rank R still equal to 2, the null space dimension is 3 minus 2, which equals 1. That means the null space of A transpose is a 1-dimensional line in R3 spanned by the single special solution, -1, -1, 1. The key takeaway is this. More columns create more room for free variables, which leads to a larger null space. The dimension formula n minus r shows that even with the same rank, a different number of columns produces a null space of a completely different dimension. Here's a summary of everything we've built. First, the key theorem. The dimension of the null space equals n minus r. That is, the number of columns minus the rank. This tells you exactly how many special solutions you'll find and how many dimensions the null space has. Second, the recipe for finding a basis. For each free variable, set it to 1 and set all other free variables to 0. Then back substitute to solve for the pivot variables. Record the resulting vector, that's one special solution. Repeat for every free variable. These special solutions span the entire null space, and the identity block that appears in the free variable rows guarantees that they are linearly independent, so together they form a basis. Third, each special solution doubles as a column-dependent certificate. It reveals which columns are redundant and exactly how they combine with other columns to produce 0. Coming up next, solving ax equals b, where the right-hand side is not 0. The null space still plays a starring role.